All right, so yeah, today is the lecture number 3, and today we're gonna discuss divergence. We will continue discussing divergence and its importance for electrodynamics. Then we will also discuss curl operator. This is the last one. Curl operator, Laplace operator, circulation, and Dirac delta function. Dirac delta function. Let me. So guys, please keep your mics muted. Dirac delta function, and as a first thing from electrodynamics, we will touch upon the concept of charge density function. Charge density function. Okay. So yeah, but before we come to the curl, let's continue the discussion of the derivative, right? And it was problem number 2, and we start with discussing the field flux. Or flux of a vector field. Okay. So by definition, flux considers the flow of the vector field through some area in space. So for example, if I take the area like this with area surface S, and suppose I have some field that flows through this surface S. Okay, and this is the field A. Okay, so the definition for flux, so F, right, is noted by this Greek letter F. Flux is the dot product of the field times the vector of area of the surface. So what is vector of area of the surface? So in order to, so the area, of course, of any surface is determined by not only the area itself, but also by its orientation in space. And the best way to define the orientation of a surface in space would be to assign an orthogonal vector to this surface. And we assume this vector is unitary, so the absolute value of this vector is 1. And the vector of the surface is equal to the absolute value of the surface, which is the area, right, times the unit vector. Okay, so this vector describes not only the area of the surface but also its orientation in space. Why it's important? It's important because, for example, for this vector field, I can arrange my surface like this with n along the vector field. And in this case, the flux will be maximum, right? Maximal, and this obviously. But I can also arrange this area, this surface, like orthogonally to the flux of the vector field, like this. And in this case, this flux will be minimum, and actually it will be equal to 0. So no flux going through the surface. So we need to define the area by its vector in space. All right. So far this is fair for the area of arbitrary value, and of course we need to define the flux through infinitesimally small amount or infinitesimally small part of the surface. And the way we do that, we basically push the size of the surface to 0, and this flux becomes the df, right? And is still equal to the scalar product of the field in this point times the element of the surface. So this is the flux element. Extra x flux element. Okay, so that if the field is inhomogeneous, if it depends on the direction in space, I mean the coordinate in space, then for any surface, for any arbitrary surface, the actual flux will be given by the integral of the flux element. ds over the surface. Okay, so this formula given through the integral is fair for any type of field and any type of surface are arranged somehow in that field. Okay, so let us consider a little bit more this vector of the surface. Okay, so this is so yeah, let's consider a coordinate system like z, y, x. Okay, and let's arrange this element of the surface orthogonally to the axis y. So the normal of the vector of the surface is along the axis y. Okay, so in this case, this element of surface is defined by dx, right? So this element parallel to the axis x, and the element dz. Okay, element is parallel to the axis z. Okay, and by the definition of the area of the rectangular element, it will be equal to ds, and I put y here to denote that this is the element orthogonal to the axis y, right? And it's equal to dx dz. Okay, and now if I want to turn this element of the surface to the vector, I multiply this by vector n unitary, but in our case, this n is parallel to the axis y, which means that this element is defined by the unit vector of y, which is j. Okay, so this is the element of the area orthogonal to the axis y, and it's defined by dx dz and the unit vector j. And the same way, if I consider the other two elements of the surface orthogonal to z and x, I will get the other two elements of the area. For the x, it will be dy dz, obviously, and times I vector. And finally, for the z, dx dy times k. Okay. So now, since this is a vector, and we just wrote down all three components of the vector, I conclude that for the arbitrary element with the arbitrary orientation in this space, this element of the area will be given by the sum of these three. So it's going to be so let's start with x. For the x, we have dy dz times I plus for the y, we have dx dz times j, and then plus dx dy times k. Okay, so this is the formula for the arbitrary oriented element of the surface of the area in our three-dimensional space. Okay, and hence, going back to the definition of the flux element here, which is the dot product of the vector A times ds, we recall this formula for the dot product, right, of any two vectors, a, b, which is ax bx plus ay by plus az b bz. So we conclude that the element of the flux is equal to ax dy dz plus ay dx dz plus az dx dy. Okay, so this is the element of the flux of field A through the arbitrarily arranged element of the surface in the space. Okay, so now let's consider the total flux through the enclosed surface. For example, let's consider axis x, okay, and two orthogonal areas to these elements of the areas orthogonal to this axis x. We of course have some field in the space, and this field comes inside this space defined by this, between these two elementary surfaces, right? It goes in, and then it goes in through the first wall and goes out through the second surface. Okay, and the total flux through the whole surface will be given by the difference of the two, because through one of the walls it goes in, so the flux is positive, but through the second wall it goes out, so the flux is negative. And the total flux through this elementary volume will be given by the difference of the two. Okay. So for the element of the flux through the element of the surface parallel to the axis x, it is equal to I return to this formula here. So it's going to be ax dy dz. Okay. And now, and by ax, I refer to the field amplitude at the element 1, right? So now I jump to the point of location of the second wall, the second surface, and suppose this point is x, so this one is x plus dx, right? So the x changes by dx by very small amount of x. And in result of this, the field AX, this component of the field AX, is changed by the amount of DAX. And I remind you that this dx is the differential of the of the corresponding component. So since we jumped along the axis x, so we need to take only into account only the dependence on x component. So it's gonna be dax over dx multiplied by the change of x. Okay, so I conclude that for this flux through the second wall, which is located at the coordinate x plus dx, it is given by ax plus dax, and since the element of the surface is still orthogonal to axis x, so it's multiplied by dy dz. Okay, so now I plug in this change for the field to this formula, and I get ax plus dax over dx dx dy dz. Okay, and so this is the flux through the second surface, and as I said, in order to obtain the total, so let's put this t index, so it denotes total flux through the element of the volume orthogonal to the axis x. So that's why I put this x here. So it's the difference. I subtract this one from the second one. Okay, and what I get ax plus dax over dx dx dy dz minus ax dy dz, and I notice that these two guys, they are the same and cancel out each other, so it's equal to dax over dx dx dy dz. Okay. But this is only for the element of the volume orthogonal or with the normal along the vector, the axis x. And we can go ahead and write the same formula, but for the y and z, right? So for the y, it's gonna be day over dy, dx, dy, dz. It doesn't change. And for the z component, we're gonna get daz over dz, dx, dy, dz. Okay. And finally, the total element of the flux through arbitrarily oriented element of volume in our field is given by the sum of these three. Right. So the total the total flux is equal to the flux through x, the flux through y, and and the element of the flux through z, and is equal to, I just plug in these three formulas we just obtained, and I can take this dx, dy, dz. They are the same for all these three components out from the parentheses. So I get dax over dx plus day over dy plus daz over dz, okay, and multiplied by dx, dy, dz. Okay, it's pretty interesting formula. So first of all, dx, dy, dz, it is the element of the volume built by the dx, dy, dz sides, right? And this guy in parentheses, we defined last time, yes, this formula here. So it is equal to divergence of the vector field. So it is, well, it is divergence of A, or we can also use this nabla dot A. So this is divergence of the field. Interesting result that says that the element of the flux through arbitrary oriented element of volume in the field A is given by the divergence of the field times the element of the volume. Okay. And now we can integrate this formula over the volume. Like if we have a large object placed in the vector field A, like this, right? So we have large object. We can discretize this object by, like this, by small pixels, or better say voxels, like volume pixels, right? So each voxel here is a element of volume, like each one, for example. Let's consider, for example, this small one. So it is dx, dy, dz volume. So it's an element of volume dv, right? And the flux through this particular element of volume is given by this formula. So in order to define this flux, instead of integrating it over the surface, you can calculate the divergence of that field and then multiply by the element of the volume, and that gives you the element of the flux. And since flux is the scalar quantity, you can simply sum up all the contributions from all these voxels. of from this volume. And mathematically, it means taking the integral of this formula over the volume, right? So it's gonna be the integral of third order, so basically three integrals here, then the divergence of the field dv. Okay, so this formula deserves to be framed. All right. In the same time, for the same object, the total flux is given by the basically by the surface of this object times the vector field. Okay, so mathematically it means that the same flux, just the same flux from this through the same object, is given by the surface integral. And since this object is it has enclosed surface, so the surface is closed, right? We put this circle here. So this is the circular surface integral, and it's given by this vector, the field itself, times the surface. Okay, and since these two formulas are the same, we can equal them to each other. So it gives us a very important formula. Very important formula. So let us put it in parentheses. Yeah. So this is known as Gauss theorem. Gauss theorem, also known as divergence theorem. Divergence theorem. Okay, so basically this formula tells us that for any system, for any object, if I need to find the flux through that object, instead of taking the integral over the surface, I can simply take the integral over the volume of the divergence of the field. And usually these integrals of volume over the volume are easily taken. And so this is the importance. And of course, it has other important applications, which we will discuss in what follows when next week we will start discussing the Maxwell equations. So this Gauss theorem plays a key role there. All right. So at this moment, maybe we can consider a few objects like spherical surfaces. Okay. Second, maybe another one with with three different cases of the field. For example, for this enclosed surface of the object 1, let's say it placed in the field going like this. So it is in homogeneous field, but we notice that the number of field lines that enter the surface equals to the number of lines that go out from the surface. And this simply means that the flux of this field is equal to 0. Okay. At the same time, let's consider another case when we have, for example, two charges inside of this spherical surface with plus and minus. So plus creates field, minus absorbs field. So the field lines go like this, right? So it can go out from the surface like this. Okay, so some of these field lines, they are inside of the spherical surface. Some of the field lines go out from the surface. But again, even for this case, the number of field lines that go out equal to the number of lines that go in, which makes the field flux again to be zero. So no net flux. Okay. And in contrast, for example, if I consider only one charge located somewhere inside the surface, let's say plus charge, right, it creates only these field lines that go out from the surface like this. And in this case, I mean, obviously, we have no field lines that go in, only lines that go out. And in this case, the flux in equal to 0. And we actually can even calculate this flux. So, right, so by definition, the flux of the vector field is the integral of this field. So this is field A, over the surface. And the key point here to notice is that in this case, due to this spherical symmetry of the problem, the field amplitude at the surface of the sphere is equal in each point on the surface, which means that the field amplitude is the same. It doesn't change. It's basically a constant. So we can take it from the integral like this, and then the integral over the surface turns into the surface of the spherical shape, right, which is 4 pi times r squared. Okay, so yeah, this is the flux for one charge located in the center of spherical surface. Okay, so now we can consider maybe a couple of problems. So let's consider problem one. So yeah, so last time we considered several problems about calculation of divergence. So instead of considering other problems about divergence, let's consider this example, which is quite important for the rest of the I mean for the future. So let us ask what is divergence of the product of scalar function and the vector function. Okay, so what is this combination? F is F and A are scalar and vector fields. Okay, so the product of scalar function and vector function, of course, is a vector function. And since this is a new vector function, we can take the derivative of this field. But at the same time, we cannot just take this f from the divergence because it is not scalar, right? It's not scalar. It is scalar function. It depends on coordinates. So we need to basically consider this this operation, and so the first thing, let's define what components this field FA has, right? So due to the fact that F is scalar, we simply multiply F by each component of the field A. So this is X component, this is Y component, this is Z component. Okay, so this is the components of this field FA. Okay, so let's go ahead and find the divergence of this field FA. So divergence is d over dx, d over plus d over dy plus d over dz. The sum of the partial derivatives of each component. So d over dx fax, this is the first, plus d fay over dy, and then plus d faz over dz. Okay, so this is just by definition of the divergence. So now I take this differentials by the differential of two of product of two functions, f and ax, f and ay, f and az, right? So it's gonna give me the first, let's take the divergence of f. So it's gonna be df over dx times ax plus df over dy times ay plus df over dz times az plus, and now f times the derivative of ax, ay, and z, ax plus f day over dy plus d plus f daz over d over dz. Okay, so this last one, this last line, if you take f is common here, it's multiplicator, so we can take it from the parentheses. It's gonna give, it's equal f times dax over dx, day over dy, daz over dz. So it is the divergence of vector a. So it's gonna be f divergence a. Okay, and this one, the first line here, is nothing but the scalar product of gradient of vector field of field f times the vector a. So easily seen. Okay, so it's gonna be, I mean, as a result, it's gonna be f times divergence a, f divergence a, plus a gradient f, Okay, so it's quite useful formula. So let us rewrite this like a formula. Okay. Yeah. So this is the first problem we have considered. So in order to take the derivative of the product of scalar function and vector function, we take the it's equal to the sum of the product of scalar function and the divergence of vector function, and the vector function times the gradient of scalar function. Okay. And even more important problem number 2. Problem number 2. So what is the divergence of a gradient? Okay. So even though f is scalar field, and we cannot take the divergence of scalar field, but the gradient of scalar field is a vector, and we can take the divergence of this vector, this gradient f. And so what it is, right? So for the so we can just directly calculate this by recalling what is the gradient of field f. It is df over dx times I plus df over dy times j plus df over dz times k. Okay, and we need to take the divergence of all these terms. So before we do the calculations, so divergence, I mean, again, so we have the divergence of the product of two terms here, the divergence of f and the unitary vector, right? So what is the divergence of unitary vector? Unitary vector is a vector, and we can, of course, consider divergence of unitary vector of I, j, and k. And so divergence is d over dx of the x component of the vector of the field, right? And our I unit vector is a vector that is along the axis x. So along axis x, it gets only, I mean, it gets one absolute value, the component, and 0 for the y and z, of course, right? So we have only one component like this, and of course the derivative of constant by any variable is 0, so it's equal to 0. And the same way for the j and for the k, all these are equal to 0. So now we need to take the derivative of the unit vectors. Okay. So let's continue here. So we just take the unit vectors from the vector operation. So it's going to be I times the nabla df over dx, right? Then plus j nabla df over dy, and plus k nabla df over d over dz. Okay, so now this df over dx is a constant, is a scalar function, is a scalar function. And then we have to consider this combination of nabla with the scalar function as a gradient, right? So now it is a gradient. And for the gradients, we have the d over dx of this scalar function, df over dx, and times the unit vector I, right? And of course, we would need to write for the y component x df over dx times j, and the same for the k. But when we will take the product of these terms with this unitary vector I, all the I j and I k will give us 0 because the vectors are orthogonal. So no need to calculate these terms here. And so we write it like this. And the same holds for vectors j and k. So for the j, we also get d over dx, df over y, of course, y over y, and the same for k, d over dz, df over dz, like this. Okay. So I times I gives us scalar 1, and the same for the j, and yeah, because j here, k here. So and the partial derivative by x of df over dx gives us the derivative of second order by dx squared, and the same for dy squared, plus the same for the dz squared. Okay, so this is very important result, and let us again write this in the frame. So the result is the divergence of gradient of scalar field is equal to d2 df over dx squared plus d2 f over dy squared plus df over dz squared. Okay. So on the other hand, as we know, nabla is given by id over dx plus j d over dy plus k d over dz. And what if we consider the product of two nablas, right? Product of the scalar product of two numbers, two nablas. So nabla squared. So it's gonna be nabla times nabla, and again I times I equals 1, and this component survives, but all the other components like I times j, I times k, j times k, they all equal to 0. So the result is d2 over dx2 plus d2 over dy2 plus d2 over dz2. Okay, and this is known as the Laplace operator. And comparing these two formulas here and here, we conclude that the divergence of gradient of scalar field is equal to the nabla squared of f, and it's the same as the Laplace operator of f. Okay, so let us. So it is known as Laplace Laplace operator or Laplacian. There is another name. Laplacian. So it's a nabla squared or this combination of the second order partial derivatives by x, by u, and y, and by z. Very good. So now let us transit to the curl. And the way we introduce curl, which is the cross product of nabla times vector field, right? The way we introduce curl is considering two different types of fields. Okay, so there are two types of vector fields with circulations and without circulations. Okay, so there are two types of vector fields, namely let's name it irrotational, meaning rotationless, right? No rotations. Irrotational, it's also known as curl-free field. And solenoidal field. Solenoidal field. Also known as divergence-free. Divergence-free field. Okay, so the first one is irrotational. The second one is solenoidal. Solenoidal field. So for the, example of irrotational field we already considered. For example, this is the electric field from, or a field from the charge. So right now I'm trying to avoid these names of the fields, because this theory is it works for any types of fields, for acoustical fields, for hydrodynamics, for any types of fields, for deformations. So this field is obviously, apparently irrotational. No rotations, no vortices, no curl in this field. Okay. Another example of such a field would be something like this, right? So again, no rotation. So field A. And as we discussed, this irrotational type of field is well described by the divergence of the field. Like this one has no divergence because the flux equal to 0. That means that divergence of this field is also equal to 0. Okay. Here the flux is non-zero and the divergence is not 0. In fact, it's equal to the charge of this. We will discuss that. So this type of field is well described by divergence. But what about solenoidal field? A solenoidal field can look like, for example, like this. So we're gonna have a vortex. A vortex. So it's basically rotation of the field. So this is another type of field. It's called solenoidal or divergence free. If you put your any enclosed surface, right? Any object inside this field, the flux will be always equal to 0, because this field doesn't diverge. It doesn't get any charge. So this type of field doesn't need any charge. So divergence is 0, divergence free. But if divergence free and gradient, we cannot use gradient for describing this type of field. How we describe this field? So before coming to the point, let us describe an example of such field. A systematic example of such field is a field with two-dimensional field with components minus y and x. Okay, so minus y and x, it is the field exactly like this. Let's say this is axis x, this is axis y. The field grows in amplitude. In the center, in the 0, 0, it's equal to 0. And as you go away from the origin, it grows linearly in amplitude. And for example, at some point x, right? The x component, the x component of this field is minus y. So it's directed like exactly like this. At the minus x, it is directed in the opposite direction, and for the y, along y, we've got component plus x and minus x. So it's indeed the circulation, just like a vortex of the field. Located in plane, so xy component. Okay, and what if I take the divergence of this field? So divergence is dax over dx plus day over dy, and as I can see, the x component is equal to y, which is, the divergence is 0, and the second is also 0, so divergence is 0. The field exists, but divergence is 0. Hence, this name divergence free field. So no divergence. No divergence. Then how to describe the divergence free field? Well, we have the last combination of nabla and the vector, right? Nabla cross A. And as we already know, this is called curl. And by definition of the cross product, I refer to the first lecture about the products. So the cross product is given by the the combination of I, J, K, right? Then D, dx, dy, dz. This is components of the nabla, okay? And x, y, and z of the components of the field. Okay, and again, I refer you to the first lecture. I can rewrite this by components. We can do Yeah, and so let's write that this is a curl, and I can rewrite this formula in the, by component way. So the curl of A is the same as nabla cross A is given by. So remember, the components in this formula, they go from X to Y and Z, like cyclic exchange, right? From X to Y, from Y to Z, from Z to X. And for example, for the X component, I write I, which is X unit vector. Then in the parentheses, the next term should be Y, and which is Y component of the nabla operator. So it is d over dy, and times z, right? Z component of the field. So it's gonna be a z, and then exchange of z and y, day over dz, then plus j. So j is y. So for y, next one is z. So it is d over dz. And the next is x. So x component of the field. Then minus daz over dx. Okay. And finally, plus k. K is z. And the next one is x. So I write d over dx. Then a y, because y is next, minus dax over dy. Okay, so this is the formula for the curl by components. And as you can see, it's pretty easy to remember this formula. So let us consider this example of the divergence-free field, right? So this one, which is minus yx. So let's go ahead and write the expression for the x component. X component is of the curl is this one, right? This is x, this is y, and this is z. So I'll write the expression for the x component of this field, which is d over dz dy minus day over dz. So az is equal to 0. So my field is in xy plane. Dy over dz is also equal to 0, so it's equal to 0. The same, likewise, for the y components, I get dax over dz is equal to 0. daz over dx also equal to 0, so it's also vanishes. And lastly, for the last component, for the component z, I get day over dx. Let me write it step by step. Day over dx minus dax over dy, right? Day over dx. So y component is here, x. So it's gonna be 1, and minus 1. So it's gonna be 2. Okay, so the curl of this field, is 0i plus 0j plus 2k. Okay. So this is the vector is which points along z direction. For example, as we know, this field is located in xy direction, right? This field, let me draw it like this. So this is in plane. So this vortex is in plane, like this, with the center in the coordinate origin. And for this field, the vortex in xy plane, the curl is directed like this. The orthogonal, it's orthogonal to the field. So you see, it's like a vector that defines the direction of surface. So now we have this surface of the field with vortex, and we get this curl orthogonal to the surface, and it defines basically the rotation, the circulation of this field. So yeah, so we can use the curl to describe the solenoidal field, the field with vortices, rotations, etc. So when we were talking about divergence, after introducing divergence, we also discussed flux, right? The flux is the integral quantity that describes the curl-free field. So for this divergence-free field, we also need this integral quantity, and this integral quantity, this integral characteristic, is known as circulation. So let us write this down. The integral characteristic that characterizes okay, a solenoidal field is known as circulation. 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 So what is a circulation? So let's consider a field of arbitrary shape like this. And in this field, I have 2 points, like one point and another point. And I move from the point P to the point Q by trajectory like this. Okay. And in each point of this trajectory, I get the field strength like this. Okay. And I want to know the total contribution of this field while I'm moving from the point P to the point Q. Okay. So now I'm moving along this line, and this is the path integral. And the path, in order to introduce the path integral, I need to introduce the. So let's say my step is dl, right? So this is the element of the path dl, and I'm moving in direction of unit vector n. So this unit vector n defines the direction of the motion, and the element of the, of this moving along this path, along this line, is defined by both the direction, which is n, the unit vector, and the element of the step, dl. Okay, and the circulation by definition is was denoted by C. Circulation between P and Q is given by the integral from P to Q of the vector field A times dl. Okay, and this dl is again the element of this path. Okay. So this is circulation. Circulation. Our circulation integral. And obviously this circulation integral is associated or linked to the curl. And now we need to define how it's linked to the curl. So let us write this question down. So how the circulation is linked to the curl. How's linked to the curl? It's very easy to derive this. So again, let us consider a three-dimensional space with axes x, y, and z. Okay, and I assume that we have some kind of field in this space. This is field A. Okay, and now I consider an element of rectangular path in this space oriented orthogonally to axis z. So this path gets the size along x, then along y, then along x again, and then along y again. Oops, maybe this one is not very good. What's going on? Okay, this is the second path. So let's give the name to these points. So it's gonna be P, Q, R, S. Okay, and we make this path to be like very small. So the size is equal to the step, to the small dx and dy elements, dx, dy, and we assume that we go around this like counterclockwise, like this direction. Okay, like this direction, and write elements for the circulation as we go. Through along this path. So for the PQ element, for the DCPQ element, this it's equal to the product of the the field times dl, right? So dl vector. So now this dl is directed to the positive direction of axis x, right? And it's by value, it's equal to dx, okay? And it points to the in the x direction. So the product of a and dl in this particular case is equal to ax dx, okay? So let us write it here, ax dx, okay? So now I jump from from this point, from the Q to the point R, and this jump happens along axis Y. So my field component dx, or sorry, ax, is changed by the element dax. But since this change happens along the coordinate y, this change is given by the partial derivative of ax by dy, because the only y changes, dy, okay? And also I noticed that dl, which is again dx, for this path rs, right? So it's directed to the opposite direction of axis x. So it comes with the negative sign. So for this dcrs, yes, it's equal to minus because of minus dx. Then the field component, which is ax plus dax over dy dy, and multiply by dx. Okay. So the sum of these two circulations, dcpq plus dcrs, is equal to, so again, I not, so I take the sum of this one and this one. So these two ax dx here and here, they come with the opposite sign, so they cancel out. And the left is dax over dy dx dy. All right. So the same can be written for the change along, for this path from Q to R and from S to P. So let me write down this. The duration goes the same way. So dcqr plus dcsp, right? SP is equal to dA y over dx dx dy. Okay, and the total circulation around this path is equal to, so that's total for the z oriented element of the path is equal to day over dx minus dax over dy times dx dy. Okay, and we already recognize this is the which one? The z component of the curl. Okay, so it is z component of the curl. And by analogy, we can write again. So let's rewrite this element of circulation through this z component of the curl dx dy. And by analogy, we can write these elements of circulation by, for the x component, it's gonna be x component of the curl, and then dy dz. And for the last one, it's gonna be y component dz dx. Okay. And of course, the total circulation for arbitrary oriented path in this space is given by the sum of all these three components. So for the total, let us write the total. Let us write curl x dy dz plus curl y dz dx plus curl z dx dy. Okay. And again, recalling this formula for the element of the surface dx, dy dz I plus for the j dx dz j plus dx dy k. Right, so this is the element of the surface. Which surface? Basically, this one, this oops, sorry, this surface, surrounded by this integration path. And I immediately recognize that this formula here, this one, can be written as a scalar product of two vectors. Like this, right? So the first component, the first vector will be the curl with components x, y, and z. And the second vector is the element of the surface. Okay, so I conclude that the total circulation through the arbitrary oriented path in the space is equal to the curl of the vector field scalar product by the surface S. Okay. Okay, so this is already interesting, and I recall the formula for the flux, for the element of the flux, which is like the field, right, times the element of the surface. So this is the same, but as a field, we consider the curl of the field. So we can write the formula, the circulation as an integral of this formula over the surface. So it's gonna be integral over the surface. Sorry, the curl A times ds. So it's integral over the surface. And on the other hand, by definition, the circulation over the closed path is given by the loop integral of this field by dl. Okay, so let us put this formula in frame. Okay. So this formula, this theorem bears the name of Stokes. So it's Stokes theorem. Stokes theorem, also known as Curl theorem. Curl theorem. In your third homework, you assigned. Actually, I don't remember whether you're supposed to be assigned a couple of problems about this Stokes theorem. So basically, Stokes theorem tells us that if I have an arbitrary loop like this, okay, in our closed loop, in arbitrary field, like this is my arbitrary field, this is the arbitrary loop, okay, and say I am interested in this circulation of the field over this loop. By definition, of course, I can take the integral of this field as I move along this path. But alternatively, I can discretize this surface, the area enclosed by or surrounded by this loop, like this. So in this way, in this case, it is really pixels. So it's flat pixels. And I can write, I can find the curl of this field. I can find the flux of the curl through each pixel, through this mesh cells, okay? And then, since flux is a scalar number, we can just, it's additive, right? So we can just sum up all the fluxes through all these pixels, and the result will be the same. Okay, so importance or physical meaning of this circulation is so it basic circulation. So it's equal to, for example, it's equal to electromotive force in the circuit theory. Okay, so this you have a battery, you have some, so you put your battery somewhere here, you connect this to the wire, to the circuit, and basically the the circulation over this wire is equal to the electromotive force of the battery. We will discuss that maybe next week. And I mean, of course, all these things, all these theorems and quantities theorems, they have concrete consequence and concrete meaning in what follows. And of course, before starting doing the numerical simulations, we need to go through these concepts to refresh our knowledge. Okay, so so what I gonna do? I gonna describe I gonna take an example or kind of problem. Again, we consider the same field, divergence-free vortex field. Yes. Mm-hmm.
Yeah, we are trying to sum up the field vector by finding through a small area and summing up to get the overall, right? What does it have to do with the the line, the arbitrary line we draw in the first case? Like what we are trying. I didn't get like what we are actually trying to get by doing that. Like, can you give us some practical example or related thing?
Yeah, so importance of this theorem is that instead of taking the integral over the closed path of a known vector field, instead you can find the curl of this field and calculate the flux of the curl of this field through the surface, through the area encircled by this blue path. So yes, physically, yeah, I mean mathematically, it is equal to this integral over the surface, and you discretize this surface, this area, by small ds, and find the dot product of curl and vector ds. So it's not vector anymore; it's a scalar, and each pixel gets assigned a scalar with, I mean, of course, with plus and minus, positive, negative, and then what you do, you just sum up all these of these numbers there. When you run simulation, the program really discretizes the space, the surface, the area, then calculates the field, then calculates the curl in each pixel, and then sum up the all contributions through each pixel. And of course, analytically, for the given function, I mean, for the given vector field, we can analytically find the curl, and then can calculate this integral, and so we don't need really sum up all these contributions, right? The result will be given like automatically. And the point, of course, is that finding surface integrals easier than finding the path integrals. I mean, usually, of course. Okay, so example is here. Let us find the circulation for this field through, I mean, over the circular path of radius 1. Okay, I mean, so it's typical set for the problem like this. So the first thing we do, we find the curl of this field, and it's already defined, right? So it's equal to 0i plus 0j plus 2k. Or, I mean, in the column representation, it's equal to 0, 0, 2. Okay, so this is our curl. In order to find the circulation, we can consider only the z component. The others are vanished. So for the z component, I have 2k vector and then ds vector. Okay, so now we have this dot product of k and ds. So our ds is arranged along, so this is ds, and it's arranged along k. So it is the scalar product of the two. The absolute value of k is 1. And of course, I can take 2 from the integral. So it's 2. And then the integral over the surface. And the surface I remind you that, but it's givens, right? The radius is 1. So the area of surface with radius 1 is equal to p squared, right? So p r squared, So it's going to be 2 pi r squared, and if r is equal to 1, so the circulation is equal to 2 pi. This is the answer. Yeah, so it's pretty easy to calculate in this particular case. So let's consider another example, example 2. Example 2. Yeah, it's kind of interesting. So what is the circulation of a gradient of a field? Circulation of a gradient of a scalar field. Right. So suppose we have a scalar field f depending on x, y, and z, right? And we can find the gradient of this field, and for this gradient we can write the Stokes theorem. So it's gonna be the flux of curl of the gradient of field f times ds over some surface, and it's equal to the loop integral, the path integral of df. This is my field, dl vector. Okay. On the other hand, we know that we know the integral gradient theorem, right, which is given by this expression pq gradient f dl is equal to f in the point q minus f in the point p. Okay. So now can we compare? We look at this formula here and notice that our integral now is the closed integral, which means the initial and ending point coincide, which makes this integral 0, right? F in one point minus f in the same point is equal to 0. So we conclude that for any scalar field and for any loop, any surface, the integral, the flux of the curl of the gradient through any arbitrary surface is equal to 0. And since the surface is arbitrary, this can be only if the curl of the gradient is equal to 0 is equal to 0. So this is the answer. This is the answer. So this is interesting because it says that curl of any gradient, like any gradient, is always equal to 0. So gradient is or gradient doesn't have a curl. So a gradient field has or can't have vortices. It is curl-free field. This is quite interesting and important. And let's consider another relevant example. Sorry, let's use blue. Example 3. Divergence of a curl field. Divergence of a curl field. So what is divergence of the curl field? So again, by definition, divergence is given by nabla dot, and then curl is given by nabla cross of vector field A. Okay, so by definition of divergence, it is d over dx plus d over dy. So it's going to be d over dx of x component of the curl, right? Then plus d over dy, y component of the curl, and finally d over dz, z component of the curl. I omit the arrows for the vectors for simplicity and also to make it tidier. Okay, so let's consider these components one by one instead in different colors. So the first one is d over dx, the curl of ax. Okay, so the component x of the curl is equal to d over dy az minus day over dz. Okay, and the result is d2az over dx dy. I remind you that the order of the mixed derivative is it doesn't matter which order you take the derivative, minus d2ay over dx dz. Okay, this is the first term. The second term is d over dy, the y component of the curl, which is d over dy. Y component is d over dz ax minus d az over dx is equal to d2ax over dy dz minus d2a az dx or dy dx. And finally, for the last one, d over dz, d nabla cross yz is equal to d over dz. So for the z component of curl, I write d over dx ay minus dax over dy equal to d2ay over dx dz minus d2ax over dz dy. Okay, so now the first line says that I need to sum up all these components, but let's look at them. For example, this one here and this one here, they are the same but of different sign. Next, this one and this one also the same but of different sign. And finally, this guy and this guy also cancel each other. So that means that the sum of these three components, these three terms, gives us 0 for any vector field. So let us write this result. So the divergence of curl of any vector field is equal to 0. It's always equal to 0. So curl has no divergence. curl field has no charge. Okay, the curl field has no charge. And let us also write here the first result. I don't know why I cannot remove this. Can I do this like, yeah, delete. So for the curl of gradient, the curl of gradient is also equal to 0, right? This is our previous result. Okay, so these two formulas pretty useful. And at the same time, these two formulas lead to a pretty important conclusion that any field can be represented in form of gradient of scalar and curl of another vector. And this is known as Helmholtz decomposition theorem. So basically, yeah, let's write this down like any vector field can be represented via gradient of scalar field and gradient of scalar field and curl of curl of another vector field and curl of another vector field. And this is known as Helmholtz decomposition theorem. Quite important theorem. It basically says that, yeah, so we can represent a vector field in form of gradient and curl. And as you probably know or remember from basic physics or introduction to physics, the electromagnetic wave is given by electric field and magnetic field, and magnetic field is given by curl of some vector potential, and the electric field is given by gradient of scalar potential. And so this is in agreement with this Helmholtz decomposition theorem. So we decompose the electromagnetic field in electric field, which is gradient, and magnetic field, which is curl. Okay, so yeah, and maybe let's write down one formula which is, which will be used, but no, of course, no need to memorize all these formulas, all these theorems. What I need from you is to remember the physical meaning and yeah, so basically the meaning of these formulas, but not the formulas exactly. And of course, for example, for your midterm exam and your final exam, you will be able to use your class notes or maybe my lecture notes. So no worries about that. And as a final formula from these vector operators, also will be used in the what follows once or twice is this one. So one can prove that this formula holds. So for the curl of vector field A, it's given by the gradient of divergence of a field minus Laplacian A. Okay, and I remind you that Laplacian is given by d2 over dx2 plus d2 over dy2 plus d2 over dz2. Yeah, so this is the last formula from the vector operators. So in fact, this is another example of second order operator, curl of curl, and it concludes all possible combinations for the second order vector operation. And last topic for very last topic for today is called Dirac delta function. Dirac delta and this is, I mean, in this ends the introduction to basically to the field. It is the all about math basics for electromagnetism. So Dirac delta function, as you probably know already, it is, I mean, first of all, it's denoted by this delta, for example, x. X is the variable. It can be special. It can be time variable. And technically, it is not a function, but the distribution, right? Distribution. What I mean by this? So basically, delta function can take only two values, either infinity if x equal to 0 for the centered delta function, or 0 if or when x ain't 0. Okay, so the plot of this delta function would be look like this. So this is x, this is center 0, and the plot will be like 0, 0, 0 everywhere. But then as they come to the origin, it blows up to infinity, and then again 0. So it's infinity. Okay, so this very like weird function. But I also imply this restriction of normalization of this function. So if I integrate this function from minus infinity to plus infinity dx, I require it to be equal, I mean, this integral to be equal to 1, to unit. So it's normalized, even though it blows up to infinity and 0 in any other point. I define delta function in a way that the integral over the entire space from this function is equal to 1. So it's normalized function. And of course, we can shift to the left and to the right this this spike. And for example, in order to shift it to the right, I subtract the shift A. Right, so now this shifted delta function will be equal to infinity when x equal to a, and 0 other points. So it's x when x and equal to 0. Okay. And for because of the normalization factor or property, there is a formula, very important one, which says that when I integrate any function of x multiplied by delta function x minus a over dx, I get the value of this function in the point a. So this formula can be highlighted, or should be highlighted. We will also consider so-called three-dimensional delta functions. For example, delta of r of the radius vector is nothing but just the product of three: delta x, delta y, and delta z. Okay, so this is the 3D delta function, delta. 3D delta. And so why we need this delta function? Well, delta function allows us to describe systems of many charges. Let's write this down also. So delta allows us to describe systems of many charges. So instead of like keep track of each charge in the system, if the system contains thousands, billions of charges, we better average all these charges over the volume. And the way we do that, we do that through the use of delta function, and by introducing the charge density function. So it's charge density function. Charge density function, which is defined this way. So we denote this charge density function as a rho, and this charge density function, of course, depends on the coordinate in space, and it's simply equal to the summation of all charges in the system. So from n to n capital. N capital is the number of charges. Then charge of one particular charge, right? The Qi. So Qi is a charge of particle I, and then times delta R minus Ri. Okay, so this is very important formula too. Okay, and let's also write that we will need the total charge Q. So the Q is a total charge. Qi is the charge of particle I. M capital is the total number of particles, of charges, and the Ri position of the particle I, or charge I. Okay. And summation runs over all the charges. Sum runs over all charges in the system. Okay. So let's prove that this formula gives us the correct result. To do so, I consider an arbitrary system with some charges distributed somehow in the system, and I enumerate these charges like 1, 2, 3 charge. Let's denote the charges of Q1, Q2, Q3, right? Then Qi, and somewhere Qn. So all these charges, and this volume, I mean, this body gets volume V, and if I integrate this charge density function over dV over the entire volume, okay, so I can substitute for rho the formula above, so it's gonna be the sum from I to n, from 1 to n, then Qi, then delta R minus Ri, and dV. Okay, so the charge is constant, doesn't depend on coordinate. I can take it from the integral, as well as the sign of summation. Okay, so the sign of summation goes out from the integral from 1 to n, then Qi here, then integral of the delta R minus Ri dV. Okay, so now let's consider this integral closely. We have delta R vector minus Ri vector dV. So dV is dx dy dz, right? And delta R minus Ri is just delta x minus xi times delta y minus yi times delta z minus zi. Okay, so all this, I mean, this integral is represented as a product of three integrals, and all of them is equal to 1. So the product of all three gives us 1. So this integral is equal to 1, and the result is just summation over all the charges in the system, and is equal to the total charge in the system, right? So this representation of the system of charges through this function gives us a correct result. So let me write these formulas again, because they are quite important. So the total charge is given by the integration of density of the charge over the volume, and the density of charge is given by summation over all charges Qi delta R minus Ri. These two formulas quite important. Okay. All right. So this is the end of the math introduction, and next week we will discuss Maxwell equations. So that part will be presented in a, I would say, less mathematical but more practical way. With I will try to bring a lot of examples from different fields, so you see how the Maxwell equations really describe all aspects of electrical engineering, for example, from motors to other things. And yeah, and then after that we will closely discuss electromagnetism at in the quasi-static, right? Static and quasi-static, then low frequency system and high frequency systems, also with some examples. And then we will begin our numerical simulations. So let me stop the recording.